to talk a little bit about work that my group has been doing in using the darkest of galaxies. These are dark matter-dominated dwarf galaxies as probes of dark matter. Now, these are some of the big questions that keep astronomers up at night, including myself. The reigning theory of structure formation in the universe is very successful at explaining the large-scale distribution of galaxies. This theory is known as the lambda cold dark matter paradigm, and dark matter is a critical component in this theory. Okay, so dark matter provides the basic skeletal structure of the universe, a sort of scaffolding for galaxy formation. And yet, despite the successes of this very successful theory on large scales, it still does have a number of significant challenges on small scales. And by small scales, I mean subgalactic scales. So I'll talk about some of those challenges and in the work that we've been doing to address those problems. Flip mentioned that we met at KITP. So I was organizing at KITP a long-term program on the dynamics of gas and stars in galaxies in the Gaia era. And the Gaia satellite has really revolutionized our understanding of galactic dynamics. And I think it's going to help us really fulfill the promise of Galacto Seismology, right? So by seismology, of course, we mean learning about the Earth's interior from looking at disturbances on the Earth's surface. In a similar way, I think now we really have the potential to learn about the unseen dark matter distribution and dark matter substructure from analyzing the dynamics of the galactic disk. And I do this with my group primarily through controlled numerical experiments. Now, the reason why these small galaxies, these puny dwarf galaxies, are of interest to us is that they're great dark matter laboratories, right? These dwarf galaxies have very few what we call baryons, that is normal matter atoms, so they don't have a lot of gas and stars, and so things like baryonic processes, what we call baryonic processes, that is star formation or the effect of supernova feedback, is really minimal in these environments. So dwarf galaxies give you very pristine environments that are nearly untouched by baryonic processes. And in that sense, they serve as great dark matter laboratories. And towards the end, I'll talk about the future in this field, which I think the future is bright for the study of dark matter, with the upcoming Gaia Data Release 3 coming up in 2021, and DR-4 after that, and LSST, and GMT and TMT not too far down the road. So I like to start with by talking about this, and this is really going back a long way into history. But the history of hunting for dark objects, I would say, goes back to the 1800s. Okay, so in the 1800s, this guy called Urbain Le Verrier analyzed perturbations in the orbits of the then known planet Uranus. And he made the hypothesis that they're due to a yet unseen planet. And using Newtonian mechanics, he was able to calculate the azimuth of that planet to within a degree, and we call that planet today Neptune. So I would say this is really the first example of the discovery of an essentially dark object, simply from analysis of its gravitational effects on another body. So I'll remind you of some of the successes that the lambda CDM paradigm has enjoyed. So the movie that's running here on the top is from the Millennium simulation, which is a dark matter-only simulation, a cosmological simulation that begins with initial conditions prescribed from the cosmic microwave background, okay, which are very smooth, but with small fluctuations that are amplified by gravity to produce the galaxies and galaxy clusters that you see today. If you take a slice through this virtual universe, that's what you see here in the red. And if you compare it to the real observed universe, you see that theory matches up pretty closely with observations on large scales. Now, the progress in the last decade, this is a movie from the Illustrious simulation where they've now included baryons, that is, they've included gas, stars, star formation, and supernova feedback. And you see here the first generation of stars forming and exploding as supernovae, which then dump metals into the surrounding medium. But despite these and very significant progress, there are still some lingering questions that we still have to deal with. So I'll talk about some of these challenges now that the lambda CDM paradigm has faced on subgalactic scales. And there may be, and there have been, a number of solutions that have been proposed, and if we have time, I'll talk about that too. But let me first give you a sense of what we mean by dwarf galaxies. So these are some relatively big dwarf galaxies, like classical dwarfs is what we like to call them. This is the Large Magellanic Cloud discovered by Magellan in the 1500s with a stellar mass of about 3×10⁹ solar masses. If you contrast that to the ones down here, well, you'd be hard-pressed to pick out the dwarf galaxies on these color images, right? And the stellar masses here are much, much less. Okay, we're talking here about stellar masses of order only 1,000 solar masses or so. So pretty much like a star cluster. So we're really approaching the threshold of galaxy formation here. And these are the ones that we're discovering very recently. Now, one of the problems that we encounter with this paradigm is the so-called missing satellites problem. If you look at the distribution of dark matter substructure, if you look at the distribution of dwarf galaxies in a dark matter-only cosmological simulation, this is what you see. So there's really an abundance of dark matter substructure in these cosmological simulations. There are thousands of them that we expect to see. But if you go and count up the dwarf galaxies in the Milky Way, you see about some 50 or so, right? So it's this mismatch between observations and theory that's been known as the missing satellites problem. Now, another problem that's plagued this paradigm, again, on small scales, concerns the discrepancy in the structure of dwarf galaxies. So the expectation from theory is that the inner density profiles of dwarf galaxies should be quite steep. Okay, so this is the so-called cusp that's expected in the cold dark matter paradigm. But the observations seem to favor a shallower profile. Now, this is the dark matter annihilation map from Via Lactea. The reason why this difference is important is, of course, because the dark matter annihilation is proportional to the density. Here's one last problem that I've mentioned that we worked on. I'll talk about this towards the end. as you saw, the distribution of dark matter substructure in cosmological simulations like Via Lactea is highly isotropic and uniform. It's spread out all over, right? But when we observe the distribution of dwarf galaxies around the Milky Way, what we actually see is that they're distributed in a planar-like structure. So here's the disk of the Milky Way, and this is how the dwarf galaxies are distributed in a so-called vast polar structure. So why is this? Why aren't they distributed a little bit more isotropically as you might expect from cosmological simulations? So one approach I've taken to looking at these problems is by analyzing the gravitational imprints of dwarf galaxies on galactic disks as a means of hunting for dark matter-dominated dwarf galaxies and also as a means of characterizing them. I, in particular, have focused on analyzing the response, the gravitational response, by looking at the outer gas disks of galaxies. Now, this is the neutral hydrogen map, the atomic hydrogen map of M51. This is roughly the extent of the stellar disk of M51, the Whirlpool galaxy. As you can see, the H1, the atomic hydrogen, is significantly more extended than the stars. This is the atomic hydrogen map of another spiral galaxy, M83. The optical radius is about here. The diameter here of the H1 disk of the atomic hydrogen is about 80 kpc. So again, significantly more extended than the stars. So this is a summary of why I think the cold gas is a great tracer of gravitational perturbations and why we've used it to hunt for dark galaxies. It's the coldest component of a galaxy that is the most responsive. And the gas is a lot colder than the stars. As you saw, the extended gas disks of galaxies are really extended, right? They go out to distances that are larger than the optical radius by several times. So you have, in this component, you have the largest cross-section for interaction. And so therefore, you have a great calorimeter for gravity. And finally, just like dwarf galaxies, which I argued have very pristine environments, well, the outskirts of galaxies are also pretty clean for the same reasons. The outskirts have very little star formation. And by virtue of having very little star formation, there's very little effect from supernova feedback. So they're relatively clean environments. And the gas, because the gas is collisional, disturbances in the gas disk damp out on the order of a dynamical time, okay? Which is what I mean when I say a gas has short-term memory. It's pretty forgetful. Right, so you have this huge cross-section for interaction. You have this cold, highly responsive, and yet forgetful structure that you can analyze. So when we started this work, we applied this method to galaxies with optically visible companions to demonstrate the proof of principle of the method, because in cases like M51, which have optically visible companions, here's M51's dwarf satellite that sits here close to the tip of the short arm, we can check if our method gives us the right answer, where by our method I mean inferring the satellite mass and pericenter distance from analyzing disturbances in the outer gas disk of the larger spiral galaxy. So here's where M51 satellite would sit in the H1 if it had any. So the idea here is to do a grid of SPH simulations of an M51-like spiral galaxy interacting with satellites, and I'll vary the satellite mass, the pericenter distance, the orbital inclination, that is it going around in a coplanar orbit or in more of a polar orbit, the details of how you simulate the M51 galaxy. And one of the primary metrics of comparison between the simulations and the data are the low-order Fourier amplitudes of the projected gas surface density. Okay, so this is one of the primary metrics of comparison between observation and simulation to determine the best chi-squared fit, in a sense. So the movie that's running here shows the gas response as M51 is interacting with its satellite. And on the top here, we have a sequence of gas density images of the primary galaxy as a function of time. And I've marked with crosses here the center of M51 and the location of the satellite. At the time when we have the best fit to the Fourier amplitudes between the simulation and the data, that time is here. You can see that the morphology in the simulation closely matches the morphology in the real observed galaxy. And it's also at that time when the satellite in the simulated system sits close to the tip of the short arm as it does in the real observed galaxy. We spent some time trying to convince ourselves that the inference of the satellite mass and pericenter, which were the two quantities that we focused on, were robust to varying things like the initial conditions, the equation of state, the star formation prescription, etc. So in the interest of time, I'll skip that, but if you're interested, please ask me later. Now, M51 has a pretty massive satellite. It's about a 1:3 mass ratio satellite, so we did test this on systems that had lower mass ratio satellites to convince ourselves that the method worked over a wide range in perturber to primary galaxy mass ratio. So I'm going to move on now to the Milky Way. So this is the map that was released by Gaia. So you see here the disk of the galaxy, and you see the large and small Magellanic Clouds here quite clearly. I'm going to talk about now an example of what I mean by Galactoseismology. So this is a prediction that we made some 10 years ago now for a new dwarf galaxy based on this kind of dynamical analysis of the outer gas disk of the Milky Way. So I'll review that. And one exciting thing that's happened this year, and we did a press conference on this, as Flip mentioned earlier this summer, is that the new Gaia observations have led to the discovery of Antlia 2, okay, which is a very unique dwarf galaxy. It is the lowest surface brightness dwarf galaxy known. And we think that Antlia 2 may be the dwarf galaxy that we predicted. So I'll talk about that. So this is the raw H1 map of our galaxy. This is the distribution, the density distribution of atomic hydrogen in the outer part of the galaxy. This is the unsharp masked image, which means that if you go around in an azimuth and divide by the median, you can heighten low surface brightness features. And you see now clearly that the density map of atomic hydrogen in the outer galaxy is highly non-uniform, right? So there are these large splotchy features, there are these spiral structures, it's highly non-uniform. You can look at the low-order Fourier amplitudes, again, of the gas surface density in the outskirts here. And I'm plotting that here now relative to the axisymmetric or equilibrium state as a function of radius. And you see that the low-order Fourier amplitudes in the outskirts are of order 20 to 30%. That's pretty big. And it's not really possible to explain this level of perturbation in the outer part of the Milky Way in a purely isolated context. So we had to ask the question, what caused these structures in the outer galaxy? So that's the question that began this line of inquiry. So at that time, I did a grid of computer simulations, again, varying how massive a dwarf galaxy would have to be, how close it would have to get, and other parameters, other interactional parameters. And I fit, the data that I was fitting to was the data of the observed data from the Milky Way to determine the best fit computer simulation, which is the one that's shown here. So again, these are gas density images as a function of time. So this dwarf galaxy comes by, this fairly massive dwarf galaxy zips by. This is the time of pericenter, time of closest approach. This is present day determined by fitting to the outer H1 disk. And what we found from this grid of computer simulations that I did is that is a pretty surprising result, that we needed a pretty massive dwarf galaxy, a 1 to 100 mass ratio perturber with a close pericenter approach that is 10 kiloparsec or less to explain the strength of the perturbations in the outer gas disk of the Milky Way. And we didn't want to make it easy for ourselves, so we made a very specific prediction. We predicted that this dwarf galaxy would be currently, at present day, at about 130 kpc, and this is on a near coplanar orbit. So, one of the reasons why we had to invoke a new perturber is that it was not possible, at least in 2009, it was not possible to explain the observed structures in the outer gas disk of the Milky Way with the known the dwarf galaxies that we knew about at that time. So the large Magellanic Cloud and the small Magellanic Cloud, well, the LMC is about at 60 kpc. And if you use the observed positions and velocities as a constraint to determine the orbit of the LMC, people have shown that it hasn't approached closer in the past. So it's simply too far away to raise appreciable tides on the galactic disk. However, an interesting candidate is the Sagittarius dwarf galaxy. You can't see it on this image here, but because it's been heavily stripped, it's been cannibalized as it got too close to our galaxy. These are high-resolution numerical simulations that we did earlier, and here you see the tidal debris from the Sagittarius dwarf as it got too close to our galaxy, and the material was flung all over the sky. If you, again, use realistic orbits, that is, orbits derived from the measured positions and velocities, and calculate the backwards trajectory of these three dwarf galaxies. These are the three main tidal players of the Milky Way. And what I've done here is I've done a forward integration with Gadget. And this is the gas response on the left, a face-on, an edge-on, And this is the stars here on the right, again, face on and edge on. This material here, this is the tidal debris stripped from the Sag dwarf, the LMC and SMC. You can analyze the gas density response, and you find that the Sag dwarf just doesn't give you enough of a bang for your buck to explain the structures in the outer gas disk. So, so we were very excited when we heard about this new dwarf galaxy that was discovered from the analysis of Gaia observations. It's known as Antlia 2. It's towards the constellation Antlia. These are some images from the press release that was done by the group that discovered it. So, you know, as I said, the LMC is one big dwarf galaxy, right? Antlia 2 is about as big as the LMC, actually slightly larger, okay? But it's 4,000 times fainter, making it the lowest surface brightness galaxy known to date. Here's where it would sit if you could see it. So it's very, very close to the plane of the disk, you know, and so the low surface brightness and its closeness to the plane of the disk explains why we haven't seen it before. And here you see there's an overdensity of stars. You can get the distance from the tip of the red giant branch, and the Gaia observations also give us the angular velocity. So we can now construct orbits, backward trajectories for Antlia 2, and we can start to think about how this newly discovered dwarf galaxy would have affected the galactic disk. So given the measured positions and velocities of Antlia 2 as the initial conditions today, we can calculate its backward trajectory. Okay, so that's what I've done. And what I'm showing here is the pericenter distribution, that is the distribution of closest approach. And the mean value here is about 15 kpc, but there are also a significant fraction that get within 10 kpc and less. This is the distribution of the height, the absolute value of the height at pericenter as a function of pericenter, and you see that in nearly all cases, Antlia 2 stays very close to the galactic disk. That is, in other words, it's on a near coplanar orbit. So, you know, our approach here is to use test particle calculations to survey the parameter space, because the Gaia measurements now currently have large errors, so we want to take the error space into account and calculate a range of orbits that's consistent with the measurements and sample over the errors. So we earlier developed some scaling relations that give you that allow you to infer the satellite mass simply from a measurement of the strength of the Fourier amplitudes, and we showed that it scales very simply as the square root of the satellite mass. And more recently, my graduate student, my former graduate student, Andy Lipnicki, extended these scaling relations to look at the dependence of the strength of the Fourier amplitudes also on the pericenter distance. Okay, so he developed analytic relations that describe how the strength of the Fourier amplitudes depends also, on both the satellite mass and the pericenter distance. So the advantage here, of course, is that you know, you have an H1 map. You can immediately then measure, you have a number, you have a pure number that tells you how hard that disk was hit, right? So that's a pure number that tells you the strength of the Fourier amplitudes. And for a 1:100 mass ratio perturber, you can immediately back out what you expect for the pericenter. Okay. So we use the test particle calculations, which are very fast, to comb through the parameter space, and we then do a smaller number of SPH simulations. So I use codes like Gadget and Gizmo, and this is one of the simulations with a low pericenter. The gas response here again is on the left, face on and edge on, and you see the stellar response on the right. In addition to the structures that I've been talking about in the gas, you see also very, very interesting structures form in the stars. You see these ring-like structures, which are very reminiscent of something called the monoceros stream. And you see, of course, a lot of tidal debris stripped out from the Antlia 2 interaction. So what I'm showing here, again, is the strength of the Fourier amplitudes as a function of pericenter distance. And the blue points here are from the test particle calculations that span the measurements and the errors. The green points are some of the n-body calculations. And the red here is the actual observed response in the H1 disk, which you can hit if you're varying things like the equation of state. Okay, so as you're going towards a more isothermal equation of state values, you can pretty much hit the observed response. If you're using orbits derived from the Gaia proper motions that have, roughly 10 kbc or less. So the points of agreement here are the radial location, which is nearly spot on, the near coplanar orbit that Antlia 2 is on, and the mass. If you infer the mass of Antlia 2 from the mass metallicity relation, which is a correlation that we use very frequently in astronomy, you get about 10 to the 10 solar masses. It was important for us to explicitly, again, consider the case of the Sagittarius dwarf galaxy, because the Sagittarius dwarf has tidal debris, so you know that it has interacted with the Milky Way. Okay. Now, the Sag dwarf has been known about since 1994. There have been lots and lots of studies, and now we have very precise measurements of the angular space velocities of the Sag dwarf. So I'm showing here the distribution of pericenter values for an assumed gravitational potential of the Milky Way. Of course, the scale is very, very different now than the scale that you saw for the Antlia 2 dwarf. So the orbit for any assumed gravitational potential for the Sag dwarf is very tightly constrained. Sag, however, is on a polar orbit. It is not on a planar orbit, so it's well off the disk. And again, this is where the true response of the outer H1 disk is. This is the observed response of the outer H1 disk. And if you take, let's say, a value here of the pericenter, and you calculate what Sag would do to the galactic disk, how hard would it hit it? This is approximately where it sits. Okay. So it gives you a little bit, but certainly nowhere what you need to explain the structures, the planar disturbances in the outer gas disk with Sag alone. And there are two reasons for that. One is the pericenter is a little too large than what you need. And the second reason is that a polar orbit okay, even if it is of the same mass perturber, is not going to give you as much bang for your buck as a coplanar orbit. Okay? And Sag is certainly on a very, very polar orbit. So this is another example, I think, of what Gaia, the kind of thing that Gaia is really opening up for us, this new avenue of galactoseismology. This is work that my student, my current PhD student, Peter Craig, has been doing to identify moving groups, that is velocity substructures, clumps of stars that move together coherently in simulations, and comparing them to real data. And he's been contrasting different kinds of simulations. This is actually the logo that we used for our KITP program. We selected this because this is, showing these vertical waves in the stellar disk that people have analyzed to characterize dark perturbers. So what Peter has shown now in this recent work is that he's analyzed some of my old simulations, and what he finds is that close to present day, what's shown here are the velocities in the plane, and what he finds is that close to present day, the number of moving groups, they're marked here in these blue circles, in interacting simulations is significantly larger than what you see in isolated simulations. And there's some hint now, it's not completely definitive, but there's some hint now that interactions like the one that he's looked at here, which is with a coplanar interaction, very similar to the Antlia 2 interaction, give you a different distribution in the velocities in the plane relative to the Sag interaction. That is, in particular, this kind of interaction gives you a larger spread in this direction in the velocities compared to only the Sag interaction. And this kind of interaction actually seems to be needed in addition to the Sag interaction to match the distribution of moving groups in the Gaia data, actually. So another very exciting thing that's received quite a bit of attention this year is this is an old idea, but it's kind of been reincarnated, I guess. But the old idea is that if you have a dwarf galaxy and it's moving through the dark matter halo of a large galaxy, it's going to leave a wake in its trail. Just like when a ship is moving through the ocean, you see a wake in its trail. And this group now has done simulations of the Large Magellanic Cloud moving through the dark matter halo of the Milky Way, leaving overdensities and underdensities in the dark matter halo, and have suggested observing strategies of seeing this kind of dark matter wake in the stellar halo also. If you see it, this is due to the Chandrasekhar dynamical friction, which scales in proportion to the mass, a square of the mass of the satellite. Okay, so this is inclusive of the dark matter mass. So it gives you an indirect handle on, well, even the existence of dark matter. Right? You wouldn't see such a large wake if the mass of the LMC were not so large, and if the mass of the LMC did not include dark matter. So it potentially gives you a constraint on the total mass. So these are some simulations here now of the same simulations, just rendered a little bit differently, that show the stellar response as Antlia 2 is interacting with the Milky Way. And the gas here, you see a lot of tidal debris stripped from Antlia 2. Since the current measurements from Gaia do have large errors, we wanted to go ahead and make a kind of hand on the cutting board kind of prediction. So we did predict the proper motions that should be seen by Gaia DR-2 if this is the dwarf galaxy that we predicted. And basically, this gives you a very narrow range in one of the proper motions in mu alpha cosine delta, if you know what that is. Now, if this is the dwarf galaxy that we predicted, what this means is that we have constraints on its mass and its orbit because the tidal force is constrained. What is left undetermined is the density profile, and as we discussed earlier, there's this cusp-core controversy, right? There's this controversy about what the density profiles of dwarf galaxies should look like. And Antlia 2 really is very unique because it is the lowest surface brightness galaxy known. Its half-light radius is 3 kpc, as large as the LMC. And it's still a question if you can produce cores that large in the standard cold dark matter model. So maybe we really need self-interacting dark matter to do this. And I've been doing some work with Omid and Hybor here to test this. Another, I think, again, very interesting line here is looking at dark matter wakes from these passing massive satellites. And Antlia, because it is massive, may leave a very sizable dark matter wake that, again, would give us a constraint on its total mass. And its orbit is in a very different direction from the LMC. So we should be able to disentangle those two effects. Now, again, this is, I'll talk a little bit now about what we can expect in the future. Now, Gaia, of course, is really revolutionizing galactic dynamics and making galactic dynamics fashionable again by providing 6-dimensional phase space data, that is the velocities and the positions. But the distances that we get are accurate to roughly within this region here shown in the green, okay, from Gaia. Recently, at this Scilog workshop, we had the idea, this is work that I'm doing with Robin Sanderson and Dan Huber, to use astroseismic distances derived from the oscillations of stars. These are solar-like oscillations due to near surface convection that the analysis of which can give us quite precise distances. And by using these distances, we can expand the Gaia phase space volume by more than a factor of 10. So this is about how far we can get. We can get into the region to test the LMC wake, the region to test the Antlia 2 wake. And in particular, the atomic hydrogen map that I analyzed, this is the map that was derived by Levine, Blitz, and Hylas. It does use these so-called kinematic distances, which relies on an assumption of the rotation curve. So we can re-derive that map using astroseismic distances, and this is work that we're starting to do now. So this is one of the small-scale problems that I talked about earlier, the vast polar structure of dwarf galaxies. That is, the dwarf galaxies that we see are not distributed isotropically on the sky, but rather they're distributed in this kind of planar structure relative to the disk of the Milky Way. Right? So my former student, Andy Lipnicki, has used now here my orbit integration code, and he's taken the measured HST. He's taken the measured HST proper motions of the satellites and integrated backwards in time to calculate their trajectories. And what you see here is that while you, of course, you start out with a thin planar structure, but it disperses very quickly. Whether you do this calculation using only the classical dwarfs, or you exclude Leo 1 and Leo 2, whether or not you believe they're bound, or whether you only use the aligned satellites, or whether you only use the ones with the trusted, very accurate proper motions, the results are pretty similar. Okay, so what we concluded from this is that certainly this so-called vast polar structure is not a dynamically stable structure, for sure. So we think it is unlikely to pose a significant challenge to the lambda CDM paradigm. So in summary, I would say that Gaia is really opening this new window for us, and it should help us fulfill the promise of galactoseismology by allowing us to learn about the dark matter distribution and dark matter substructure by studying the dynamics of the galactic disk. And discoveries of unique dwarf galaxies like Antlia 2 are really challenging our notion of what dwarf galaxies are like. And these kind of dwarf galaxies really have the potential to shed light on the nature of dark matter through analysis of their density profile along with their dynamical effect on the galactic disk. So the missions and the surveys that are coming up in the next 5 to 10 years have really significant potential for moving this field forward. This is a paper that we wrote for the decadal survey, and what's shown here is the fractional uncertainty in the density profile when you use only radial velocities. This is as a function of stars. Okay, so if you only use radial velocities, you're not doing so well in inferring the density profile. But if you have the three-dimensional velocities, you're doing pretty well, and you should be able to infer, make the distinction between a cusp and a core with a few hundred stars. This is using the GMT and TMT. These are, in blue here, the known dwarfs today, and in pink, the projection from LSST, which should be complete, down to stellar luminosities of order 1,000 solar luminosities within 1 megaparsec, which means that you'll really have a census of dwarf galaxies around the Milky Way, and you can start to say interesting things about the amount of small-scale power at that point, which should allow us to test the nature of dark matter with these upcoming surveys in the very near future. And I'll thank my sponsors as well. Thanks a lot for your attention. Questions?
You didn't say much about it, but the Astronomy distances from Gaia allow you to go much further out.
So these are, this is work that Dan Huber has been doing with determining the distances. And what he's shown is that the light curves, these are the light curves in, let's see, so Kepler is shown here in black, and the ground-based data from Atlas and Assassin is in red. Okay, so the photometry is not too far off between space-based and ground-based observations, and when you do the Fourier transform, you get values that are pretty close for the dominant oscillation frequencies between Kepler and the ground-based observations. So we think that these all-sky time domain surveys that are being done from the ground should allow us to get pretty precise distances from analyzing these oscillations. And that's really the heart of the idea here that we can, right now, what Gaia has done is truly extraordinary. It's given us a much larger phase space volume to study than we had before, but it is limited. And so if we can expand that phase space volume, we can, as I said, we can rederive the map of the atomic hydrogen distribution for the outer H1 disk with these distances, with these much more precise distances. So we can have a real precise view of the outer gas disk of the galaxy. And we can go beyond to the mid to outer stellar halo, which should allow us to get a more robust inference of the gravitational potential inclusive of the dark matter halo in the outer galaxy as well. So that was the motivation behind that.
You started out talking about the missing satellite problem. And I'm just wondering if the results so far, and maybe especially the H1 searches,
right,
have already ruled out the possibility that the missing satellites are a bunch of dark matter only things that would stir things up, and it's not as stirred up as you would expect from CDM simulations.
Right. So, I should say also, before I answer that, I think what people would say is that if you use things like abundance matching, you would certainly be able to solve the missing satellites problem down to some mass scale, certainly the mass scale of classical satellites. What's unclear at the moment is if you can solve it down to like the ultra faints, right? And so that's really the battleground, right? The ultra faint dwarfs are where we're still having a lot of debate. In terms of the H1, when I started this, I was of course motivated by the missing satellites problem, and I was trying to develop methods to hunt for dark galaxies by analyzing their tidal imprints. What we've shown thus far, and what I think the method is robust to, are about 1 to 1,000 mass ratio satellites. So again, we have the same problem as abundance matching does. So we're not quite getting down to the ultra-faint regime either. So that really is the battleground for the future, and that's where LSST is going to make a big difference. I think there was another question here. Yeah. Yeah.
You said something about Antlia being equal galaxies. Does that imply that your perturbation analysis could have maybe multiple galaxies along the
Sorry, I said something about what?
You said something. You said if Antlia 2 is the perturbator.
Right.
Are you implying that there could be perhaps multiple perturbers that would explain the same signal? There's some degeneracy there between a single object with a certain mass and multiple objects whose mass together sums up to be?
No, not in this particular case. I mean, that could be true in general, and there are ways of breaking that degeneracy that we've worked on. But I think in this particular case, all I really meant is that, right now the Gaia data release 2 observations do have large errors, right? The errors on the proper motions are 40% and 20%. So that's why when I calculate these orbits, right, like, so when I calculate these orbits, I'm not able to pin down the orbit exactly, right? So that's why I talk about an orbital distribution here. This is a histogram of pericenters, so I can't pin it down exactly. It's still possible that this thing could have, a large pericenter. It's unlikely, right? But it's possible. So when DR-3 is released, we will have much smaller errors on the proper motions, but what we did in this paper is we did predict the proper motions that should be seen by Gaia DR-3 if Antlia 2 has this range of pericenters. So we made a very specific prediction for that, and that leads to a constraint on the, in particular, the mu alpha cosine delta values, but not a significant constraint in the other direction. Right. Right. Right.
So what makes you confident that this is actually an interaction and none of the other?
Right. Yeah. So we looked at some of these mechanisms one by one. So you can, for example, look at the effect of a misaligned or a squashed, a triaxial dark matter halo, and I did this with Victor De Battista using his simulations. These are the planar disturbances, right? We're not looking at the warp, which is a different mechanism. So from looking at those simulations, Victor's simulations, which did have misaligned dark matter halos and a significant non-spherical shape in the dark matter halo, we convinced ourselves that this amount of perturbation in the plane would not result from those kind of effects. And the simulations that I showed earlier these ones, in fact, do include the LMC and the SMC as well, and the Sag dwarf. They don't include. Yes, yes. They don't include this other perturber. So this is sort of, you could say, it's a control. Okay.
Any other questions?
So how do you determine the dark matter weight exactly? So you mean the density observation is more affected distribution of maybe gas? That's what you can see there.
Right. So there are some proposed observing strategies now that have been proposed to look for the LMC's wake in the stellar halo. You do have to look pretty far out, and I think one has to be maybe a little bit optimistic, but it's good to be optimistic. But you're basically looking for overdensities and underdensities, and Gary de Camargo et al. have looked at a number of models, have looked at a number of orbital trajectories, and suggested some of these observing strategies, to look at the. I mean, in principle, it's about a 20% effect or a 30% effect. The mass of the LMC that's assumed here is several 10 to the 11 solar masses, which possibly is optimistic. But, I think it's a very interesting idea.
Okay, so before we thank Sukanya one more time, I'd just like to impress upon the grad students, especially the young ones. I hear that potential advisors like it when students ask questions.
Thank you so much. Thank you.